Martínez. But fast estimates for clustering estimates. Is this true? No, a bit different. So he will tell us.
Fast estimates for clustering similarity. Sorry. Good evening. I am very pleased to be here, and I thank the organizers for inviting me to give this talk. This is John Ward with my master's student, Hugo Sanz, from the UPC. And the title is wrong. It's similarities. I think it's fine in the program, but I'm pretty sure most of you know that the goal of clustering is just we're given a set of data points, and we want to group them into clusters of similar points, similar being close in some metric space. Now, this clustering has tons of applications in all areas of science and technology, and in marketing and commerce and linguistics and biology, sociology, whatever. The main purpose would be classification. We want to classify, put the different input data in different classes. But they are also used in recommender systems. They are used in pattern recognition, in anomaly detection, in community detection, and so on and so forth. There are tons of applications, and there are many, many different clustering algorithms. Just some terminology. I'm not sure it's the official one, but that's the one I'm familiar with. We have some input data set. I'll use omega for that. And the data points that we will see them. They will be points in some in R to the D for some dimension D. A clustering will be a partitioning of the data set of omega, disjoint sets into disjoint sets. There are situations where we might be interested in some soft clustering where we assign to every data point a kind of function telling us what's the probability that it belongs to that class, right? But not here. We will be considering just hard clustering. Every point belongs to just one cluster. Now, given the two clusterings, we can build something called a contingency table or contingency matrix, which is just counting how many points there are in the intersection between cluster xi and cluster xj for all I and j. Of course, the sum of the entries in this matrix will be n, the total number of data points, and we will also be interested in the marginals, in the sums of the columns or sums of the rows. Now, this is just a short glimpse of the vast number of clustering algorithms that exist. They can be classified in different families, like the famous k-means and k-means plus plus, k-medians, so on. The hierarchical clustering algorithms, those maybe start with just one big cluster, and then they keep dividing it into up to the point where you are satisfied with the result, or everything is in a different cluster initially, and then you keep merging clusters until you get something you are satisfied with. The partitional go through several refinements, putting every elements into clusters. Then they redefine what's the center or the centroid or the kind of the attractor of each corresponding cluster, and then you go through an iterative process until you reach some criteria. And there are many other ideas or many other approaches to clustering. This is not an exhaustive list at all. But we are not going to be interested in those algorithms in a sense. What we are going to be interested in measuring the similarity of clusterings. To begin with, it's typical that we have some sort of metric or some sort of measure of the quality of a clustering. And the clustering algorithms are trying, in a sense, to optimize that measuring, right? So you can formalize those most clustering algorithms, like you are given the data set, maybe you are given also the number of clusters, the K, maybe not, but it depends. But the thing is that you want to find the clustering such and such for this data set will maximize or will minimize my criteria pi of x. For instance, pi could be, I want to maximize the minimum distance between points in different clusters. Okay, maybe the criteria is some other. The point is that this criteria that maybe our algorithm is able to find the optimal clustering according to pi. In some other cases, it's not possible because the problem is NP hard. So the best you can do is kind of approximate that ideal. I want to try to get a good approximation to the optimal one. But anyway, maybe this clustering that we get, the optimal one, is not the thing that we are interested in. It's not the true clustering we are thinking of for our practical purposes. So what we actually need also is to have some sort of comparing clusterings to some ground truth. How would we classify this set of things? How well is the algorithm doing? We need similarity measures, external, extrinsic metrics that compare two clusterings. And one of them will be like, this is the reference clustering, that's the ground truth. How far are we from the ground truth? How well is our algorithm doing? And there are many, literally dozens of similarity measures that have been proposed in the literature. And there's a hot debate also, which ones are the good ones, the best ones? Because again, depending on which similarity measure you pick, this will correspond with your intuition about what's a good clustering or not. Now, this is not every similarity index is in one of those families, but let's say 99% of them will fall into one of those two categories. It's a pair counting index or a information theoretical index. There are a few which are not into this classification, but they're kind of an exception. Now, pair counting indices basically are telling us that two clusterings are very similar if they agree on how they do classify a couple of points. Are they doing the same or are they doing different? So basically, they are functions of those four numbers. And 1 is the number of pairs, A, B, where are in the same cluster in X, and they are also in the same cluster in Y. And 0, pairs such that X classifies those 2 points in different clusters, and Y does the same. It classifies those 2 points in different clusters, so on. So you have those four numbers. The sum of them will be the n choose 2 possible pairs. And here you have a few very famous similarity pair counting indices. The rand index, which was defined in 71, if I recall well. That's the number of pairs for which the two clusterings agree, because they tell you basically the same. They are in the same cluster in both, or they are in different clusters in both, divided by the total number of pairs. And then there are several other indices like this adjusted index are defined from some original measure, and then you subtract, you want to remove the randomness, because if you pick two clusterings at random, they will exhibit some similarity. They will not be completely different. So basically what you want to do, you want to adjust this for chance, to remove this randomness component, and this gives you things like the adjusted run index. In the end, this is the final formula. Basically, you take the run index, and then you subtract what's the expected run index for a couple of random partitions, for a couple of random clusterings. Now, then there are this other one, the correlation coefficient, which is very close to the cosine distance. You might know from other areas of, like today we have learned about the Jacquard distance. This is the run index in the world of clusterings. Run index is like the Jacquard index. This correlation coefficient is like the cosine distance for sets. And then I have given a few more names in this long list of similarity measures that exist. And all those are pair counting indices. Now, you can define, you can express those numbers, n11 up to n00, in terms of the contingency matrix, so in terms of the AIJs, okay? And this will be convenient because if you want to count the n11 and 01, blah, blah, by going through all possible pairs, that's too expensive. And you can obtain the contingency table if you use appropriate data structures in linear time with respect to n. And if you go counting pairs, then if you follow the definition literally, then you will have a quadratic algorithm. You don't want that in n. So keep in mind that you can compute the n11 up to n00 in terms of the contingency matrix. Now, the information theoretic indices basically are telling us, oh, how much information do I need to convert x from y? If I'm given y, how many bits do I need to obtain x? And vice versa. So they are usually defined in terms of the joint entropy, the entropies of the x and y. When we see them, when we see the entries in the contingency matrix as probabilities. In terms of the conditional entropies, in terms of the mutual information, which is the sum of entropies minus the joint entropy. So again, there are functions of more or less complicated functions of the contingency matrix entries. And you have also a ton of different similarity measures, like the normalized mutual information using the sum or using the max, where you take the mutual information and then you divide by the average of the entropies, or you divide by the maximum of the entropies. And then you have also using a square root or mean or joint, you name it. You have many variants of the normalized mutual information. Then you have the adjusted variants of those normalized mutual informations, where you subtract for randomness, and you have the adjusted normalized mutual information with the sum, with the max, with the mean, blah, blah, blah. And you have also another one, which is very famous, the variation of information, which is the conditional, the joint minus the mutual information. And in any case, computing one of those similarities of two clusterings will be linear in n plus the product of the size number of clusters in x times the number of clusters. As this I mentioned. Now, why should we estimate similarities? Why don't you compute them exactly? You go, you take, you compute the contingency table, and then you compute the corresponding similarity index. Well, there are situations where it's a good idea to estimate similarities. Like, imagine you have tons of objects, many objects, and you need to compute the similarities between all possible pairs of objects. That's, for instance, something you will encounter in applications like you have many documents and you want to retrieve the most similar one, or when you are doing clustering, you are computing a lot of distances or similarities between objects. But now our objects are clustering, so it's kind of, no, we don't need to estimate similarities in that situation. That's a very unlikely scenario where your objects are clustering. However, there are situations where it makes sense to estimate similarities. One is a bit not so common, but imagine you have some data that you will classify or you will cluster using different algorithms, and then you want to reach some sort of consensus among the algorithms. And then it might be useful to have those similarity measures between the different algorithms, the different clusterings. But I think that the most interesting situation is this one. You don't have the ground truth. You have to ask the experts, right? But you cannot ask them, oh, classify me this 1 million points for me. Classify this homologous database into classes, into clusters. What you can ask is like, oh, here's a sample of the data points and give me how the ground truth clustering looks like for this sample of points. Or I'm giving you a sample of random pairs. How would you classify them? Do you agree with what was the output of the algorithm? Yes, no? That makes sense. You will work with a small sample and you can ask your expert to tell you those answers. Now, intermezzo. I'll use this theorem for the first kind of result that we get. It's basically folklore result. I have a random sample of size S, and I have some property, the ratio, the fraction, the proportion of elements in the population that satisfy the property, divided by the total number of elements in the population, is estimated by the fraction of elements in the sample that satisfy the property, right? Also, we have the variance for this estimator. It's an unbiased estimator, and the variance is basically like 1 over S. I'm writing this because S might be, the size of the sample could be a random variable, right? Now, how do we use this result? Well, for the random index, you just need to draw a random sample of the n choose 2 possible pairs, and your property is X and Y agree for that pair. Now, you count how many pairs agree in your sample, and this fraction will be an unbiased estimator for the fraction of pairs that agree in the full population, the run index. Here you have also the variance. This is because of the previous theorem, right? You have to put some care in the way to sample, to get a random sample of pairs, unless you are willing to pay a lot more and you use some kind of rejection method. But if you want to avoid rejecting pairs, then you have to put some care in, but you can do. You can get a random sample of pairs of n hat pairs in linear time. And the same reasoning that we used to show that we have a unbiased estimator for run index will work for other, like Hoover, normalized Mirkin blah, blah. But not for all of them. There are pair counting indices for which this does not work, like correlation coefficient or the adjusted rand index. Now we need to do a bit better. And well, the idea here is that most or many of them, a large number of them, they are of the form, they will depend on this vector of counts. And the function, you apply some kind of function, which is a quotient, P divided Q. Okay. Not a proportion, because maybe Q there's a square root, but it's a quotient. And now the intuition is basically, well, the expected of the similarity for the sample will be an unbiased estimate, not unbiased, but asymptotically unbiased estimator for the similarity of the population. Okay, so it's, in general, the expectation of F is not F of the expectation, but the idea is that, yeah, but here it is, or we are very close enough, especially if our sample is big enough. And then one of the things that happens is that the similarity measures that we are using most often, they are so-called homogeneous of degree 0. Therefore, basically what you have is this f of this is the same as f of n. If you multiply the vector n by whatever factor, it does not change the similarity. Okay, you can scale those counts and the similarity remains the same. But one important problem that we find is that some of those functions, sometimes the function f, like here, right, might not be defined for the full domain. Let me go here. You might have that this denominator is 0. And you can say, no, but come on, you can exclude those cases. Yeah, you can exclude those cases and you avoid comparing two clusterings where the denominator would be 0. But if you are doing random samples, how do you exclude that? That's a problem. Okay. So, well, the point will be that we do something called regularization. Sorry, we were here. What we will do is do something called regularization. Before that, just let me mention give the formal definition of homogeneous of degree 0, namely f of alpha x is f of x for all alpha non-null alpha, and many similarity measures, pair counting indices are homogeneous of degree 0. Okay, so you can scale those counts and everything will remain the same. And the regularization is done, we will use this so-called smooth bump functions, where you are given some small epsilon and you define this function, which is C infinity, and I mean, it's continuously differentiable, has all derivatives. And I'm using here Iverson's brackets, okay? So this is when the distance between x and y is less than epsilon. Otherwise, it's 0. Now, given some function, what we do is, okay, and it's defined in some subset D of the support, of the total number of all possible pairs, not all possible pairs, all possible vectors of n0 and 0, 1, blah, blah. Then we can extend by the function f by multiplying the numerator by this product of 1 minus bump functions, and the denominator, we keep the q of x plus this term defined in terms of the bump functions for all the S, sorry, stands for the support. So we consider all the points for which the original function is not defined. You can think of the points for which the Q is 0. Like the function becomes singular. And then the idea is that if you take epsilon enough small enough, then the function x will coincide with the extension whenever x is in the domain D, for which the function is well defined. The extension is well defined for omega for the full support, and it's 0 whenever the point we are given is out of D. Is one of those points for which is not well defined. Now, F, the extension F is not analytic, but it preserves the smoothness of F. And the point is that we can use it to prove the following result, but in practice you wouldn't use the extensions. I will explain this a bit better later. We need extensions to prove this theorem formally. Is like the expected value of the extension that now it's well defined will be the sigma of the expectations, right? So, and by homogeneity, you will get the sigma of the counts n0 to n1. And you get the bias, which is going to 0 as the size of the sample goes to 0. The thing is that in practice, what you will be doing is you will keep sampling pairs until either you have all them, and therefore there will be no indeterminations, there will be no singularities, but hopefully you won't need to sample so many pairs, okay? But from the point of view of the theorem, it's much more convenient to put this in terms of the extension, because remember, the extension is basically the function, the original function, but we have removed the problematic points, okay? So in particular, if I take in this idea, if I keep obtaining random pairs until I make sure that I don't get any of those factors equal to 0, that means that basically I cannot have that this is 0 or this is 0, this is, okay? Then if I have a sample for which this condition holds, I can define the correlation coefficient or the adjusted rad index or whatever, and I estimate the similarity for that without for the sample, and it's an unbiased estimator of the real similarity. I have to rush a bit. The idea is with other similarity indices. With this theorem, we are able to cover all pair counting indices that we know, like 27. And with this theorem, we are able to cover all them. For information theoretic indices, things are more complicated, more difficult. The idea would be like, oh, I get an estimation of or I get a sample, I get the contingency table for the sample, and then with some suitable regularization, my idea is that the similarity based on the sample will be this asymptotically unbiased estimator for the real similarity. And this we have been able to prove for this one that's called variation of information, but not for the others yet. We have conducted also many experiments, and here you have, for instance, that's the error with rand index as we we make the number of sample pairs grow. Same thing for correlation coefficient. You have also the standard deviation. This is for variation information. Here is not number of pairs, it's number of elements that we sample. Eventually, when you sample everyone, you get an error of 0. And well, there are some future ongoing work. Probably you can read it faster than I can tell you. And I will be glad to answer your questions.